going to record? Okay, great. So last time we were proving this theorem, which is that the right weak order is a complete meet semilattice. I'm not going to actually show that it's complete. So remember, complete means that any subset, possibly infinite, will have a meet, whereas just meet semilattice means that any finite subset has a meet, which is equivalent to saying that any two elements have a meet, because then you can just use the fact that the meet operation is commutative and associative. So I'm not going to show that it's complete, but I will show that it's just a meet semilattice, and this is also true as well. So remember, we have two elements x and y in W, and we're trying to show that the meet exists, and we're going to do this by induction on the length. So we're going to write capital E for the set of lower bounds of x and y. And we know that E, like the identity element, is a lower bound. And we can assume that E is not, well, capital E is not just the identity element, because if it was, then little e would be the unique lower bound, so it would be the greatest lower bound. So then we'd be done. So we're going to pick some element z in capital E of maximum length, and we're going to show that it is the meet of x and y. Okay, so we're going to use this fact. So we will use what I'll call star. So this is that if we have a simple reflection S, which is a left descent of some element u, and it's a left descent of some element v, that implies that u is less than or equal to v in the right weak order if and only if su is less than or equal to sv in the right weak order. Okay. So let W be some element of, okay, so my goal is to show that Z is greater than or equal to everything in capital E. So I'm going to pick some W in capital E. If W is the identity, I know that it's already less than or equal to Z, so I can assume that W is not the identity. And I want to show that W is less than or equal to Z. So I'm going to let S be a left descent of W. And I know that it has a left descent because W is not the identity. Then, okay, so S is less than or equal to W in the right weak order. So remember I said that when you have a simple reflection, it is a left descent of W if and only if it's less than or equal to W in the right weak order. These are equivalent. And we know that W is less than or equal to X because W is a lower bound, like it's in capital E, so it's a lower bound for X and Y. And okay, so, and similarly, S is less than or equal to W, which is less than or equal to Y. So this means that S is less than or equal to X, and it's less than or equal to Y, so it's a lower bound for X and Y, which means that it's in capital E. So S is in capital E, well, and it's also a simple reflection. And we proved, so I'm not going to go through this proof again, but we proved last time that this implies that S is less than or equal to Z in the right weak order. Okay. So S is a left descent of X because of this. It's also a left descent of Y, similarly. It's also a left descent of W because that's how we chose it. And it's also a left descent of Z because of this. since the length of Sx is less than the length of x, this is what it means for S to be a left descent of x. So since this is true, we can use induction, right? We're inducting on the length of x, so we know that this, the fact that we can find meets will be true for Sx. In other words, we know that Sx meet Sy exists. So let's give it a name. Let Z prime be this meet of Sx and Sy. Okay, so now I want to use star. And okay, what am I setting to be U and V? I want to use star with U equals W. And with V equals X. To get, well, okay, so first of all, I can do this because S is a left descent of U and it's a left descent of V because of this. And so this says that, well, W is less than or equal to X if and only if SW is less than or equal to SX. We know that W is less than or equal to X, so this implies that SW is less than or equal to SX. Okay, similarly, I could use star, but this time with U equals W and V equals Y to get that SW is less than or equal to SY. So what this shows is that SW is a lower bound for SX and SY. And we know that Sx and Sy have a greatest lower bound, which is Z prime. So SW must be less than or equal to Z prime. Right? That's what it means for Z prime to be the mean. So SW is less than or equal to Z prime. Any questions up to here? So I could go through the same argument, but with W replaced by Z. It still works because S is still a left descent of Z, and Z is also a lower bound for X and Y. So if you go through the same argument, but instead of having U equals W here, I would have U equals Z. You can do the same thing to show that, so similarly, SZ is less than or equal to Z prime. Now, first of all, S is not less than or equal to Sx. Why is this? It's because S is a left descent of X, so when you multiply X by S on the left, the length goes down, but then that means that S cannot be a left descent of Sx, because if you multiply on the left by S again, the length would go back up. Right, so the fact that S is a left descent of X means it cannot be a left descent of Sx. In other words, S is not less than or equal to Sx in the right weak order. And we know that we know that Z prime is less than or equal to Sx, because Z prime is the meet of Sx and Sy. So it's a lower bound for Sx and Sy. So in particular, it's less than or equal to Sx. And so this implies that S cannot be less than or equal to Z prime. Because if S was less than or equal to Z prime, then by this it would be less than or equal to Sx, but it's not. Okay, so what does this mean? So S is a left descent of SZ prime. I guess the thing that I'm using is that for any element, I don't know, I've run out of letters. for any element kappa, like S is either a left descent of S kappa or kappa, but not both. It's like a left descent of exactly one of those. And so in this case, if S is not a left descent of Z prime, it has to be a left descent of SZ prime. Okay, we're almost done. I'm going to use star again. So by star, this time with, what do I want to use? U is going to be SZ prime and V is X. So what does this give us? Well, S is a left descent of SZ prime and it's a left descent of X, so we are allowed to use star. This tells us that SZ prime is less than or equal to X if and only if Z prime is less than or equal to SX. But Z prime is less than or equal to SX because it is the meet of SX and something. So if I use this, I get that SZ prime is less than or equal to X. Yes. So S Z prime is less than or equal to X. But I could do the same argument with X replaced by Y to get, so similarly, SZ prime is less than or equal to Y. So that means that SZ prime is a lower bound for X and Y, so it's in capital E. Right, so SZ prime is in capital E. But remember, we chose Z to be an element of capital E of maximum length. So if SZ prime is in E, then its length must be at most the length of X. So thus, the length of SZ prime is at most the length of X. Or sorry, yeah, no, Z, sorry, Z. It's at most the length of Z. Okay. And what this means, so then, the length of SZ is equal to the length of Z minus 1, because S is a left descent of Z, so when I multiply by S on the left, the length goes down by 1. According to this is at least the length of SZ prime minus 1. And I know that the length of SZ prime minus 1 is the length of Z prime because S is a left descent of SZ prime. Right, so that means that if I multiply this by S on the left, I get Z prime, which has length 1 less than the length of SZ prime. Okay, so finally, let me circle what I'm using here. So I want to go back to, okay, SZ is less than or equal to Z prime. Wait, where is this? Somewhere I should say that SZ, no. This, yes, SZ is less than or equal to SZ, or less than or equal to Z prime. But then I also know that the length of SZ is at least the length of Z prime. So these two combined imply that SZ has to equal Z prime. Because if it's less than or equal to Z prime, and its length is at least the length of this, then it actually is equal to this. So SZ equals Z prime. Okay. Therefore, we have SW is less than or equal to z prime, that's this. But z prime is sz. And now I'm going to use star one last time. So use star, this time with u equals, I think I want u equals w, yeah, u equals w and v equals z. To get, well, first of all, I can use star because S is a left descent of W and it's a left descent of Z. And so now this says that U is less than or equal to V if and only if SU is less than or equal to SV. So here I know already that, according to this, SW is less than or equal to SZ. So this tells me that W is less than or equal to Z. And finally, this is what we wanted. Because we wanted to say that Z is we wanted to show that Z is the greatest lower bound of X and Y, meaning we want to show that it is greater than or equal to everything in capital E. So we chose something in capital E, we can assume it's not the identity, and we show that that thing is less than or equal to Z, so we're done. So thus, Z is X meet Y. Okay. So this is probably one of the more involved proofs that I'm going to go through in class. But I think it's like an important result. So that's kind of why I wanted to go through it. It might, I don't know how illuminating this proof is. It kind of looks like it's chasing through things. But I think there are like nice ideas here. Like the idea to induct on the length and say like, okay, I'm going to show that this poset is a meet semilattice by sort of going from the bottom up. That's sort of like one nice idea. And you know, this kind of gives sort of a feel of like how you can play around with left descents and you know, the lengths and just various things that are Coxeter theoretic to try to prove something like this. So I mean, you don't have to like memorize the proof. I did not memorize the proof, but you know, it's sort of nice, I think, to see it at least. Any questions? Okay. So let me mention that it's not necessarily a lattice if W is infinite. So if W is infinite, I'll just say joins do not necessarily exist. So it's possible to find two elements that don't have an upper bound. I mean, it's also possible to have bigger sets that don't have an upper bound. But if they do have an upper bound, then they will have a least upper bound. So, however, if X is some subset of W that has some upper bound, then it has a least upper bound. In other words, a join. Okay, so why is this true? Why do I know that if I have a set that has some upper bound, then it will have a least upper bound? This is not true for arbitrary posets. This is true for the weak order, specifically because of what I just proved.
Wait, sorry, what's the question?
The question is, so my claim is that if I have a subset of the weak order that has an upper bound, so this is in the right weak order, then it has a least upper bound. And the question is why, how do I know that?
Take like the length, the smallest length.
So, sort of. I mean, I think there's an easier way to, I mean, that would be true.
Well, you take out upper bound of the like.
Like, can you take the meat of the joins?
Yeah, you can take the mean of all of the upper bounds, right? So you say, let's just consider the set of all upper bounds for my set X. That's a subset, so it has, because it's a complete mean semilattice, which I guess I didn't prove this, okay, but that's true. So I have some set of upper bounds, I take their meat, and that is necessarily also going to be an upper bound for X. You can check that. And then that means that it's the least upper bound. Okay. So in particular, I'll just say corollary. If W is finite, then the weak order is actually a lattice. And this is just because W naught, the long element, remember there's like this long element of a finite Coxeter group, is an upper bound. For any subset of W. Okay. Any questions up to here? Okay, so this is kind of a lot. Maybe we can do something more fun. Let's talk about pop stack sorting. So, okay, where do I begin with this? Let me tell you a story. So, I think I mentioned before that I have this collaborator, Nathan Williams, who's this professor at UT Dallas. He's the one who made like the A history of lattice theory, with like all the lattice theorists moved to Hawaii thing or whatever. And so pop stack sorting is going to be a map from the symmetric group to itself. So it's some function on Sn. And at some point a couple of years ago, I was like, oh, you can just like define this for any Coxeter group. Actually, more generally, you can define it for any, I guess, locally finite meet semilattice. But you can do it for any Coxeter group. And so I wrote a paper about this called pop stack sorting for Coxeter groups. And so then, I started working with Nathan Williams, and he at some point contacted me, and he was like, oh, we could define, so there's this map that's called pop. And we could define like these other maps. We could call them crackle and snap because of the Rice Krispies. And I mean, there's not really like a mathematical reason for doing this. He just like thought it would be funny, and I was like, okay, sure. So then at some point, okay, we wrote a paper. It's called Pop, Crackle, Snap, and Pow. Oh, there's a fourth Rice Krispies elf named Pow. So okay, people don't know this, but like back in the 50s, there was like, they had this new Rice Krispies elf, and he's like a spaceman because it was like the space race or something. And it's kind of funny. He's like an elf, but he's like buff or something because he's like powerful. And so like you can find videos of this. They have like ads from the 50s. And so I guess he was like supposed to represent like the nutritional power of the cereal or something. Anyway, there's this article that was written about Pow, and somewhere in the article it says something like, lost in the shuffle, however, was a fourth Rice Krispies elf named Pow. His short life is a time capsule of an era when everyone was dreaming big. So this is Pow. Anyway, we have a paper called Pop, Crackle, Snap, and Pow. Some facets of shards. I'm not going to tell you about shards, but so okay, we presented this at a conference over the summer, and when we were making the poster for this, Nathan was like, "Oh, we should like get the Rice Krispies elf hats and like wear the hats at the poster. And I was like, yeah, okay. So I visited my family in Florida over the summer, like before this conference. And so I spent the 4th of July making these hats with my mom. So, okay, yeah, so I have the hats. So, okay, basically, yeah, okay. Well, okay, I'll get the hat in a second. Okay, so this is Pop, and this is Crackle. I don't have Snap because Nathan took it with him. It's like a chef's hat, and it says Snap on it. So anyway, I made this with my mom over like 4th of July, and then we wore it at the poster session and stuff. And then, okay, so I went back to Florida for like a week, and then I was like, I left the hats there because I was like, I'm not gonna need these, obviously, in Boston. But then I think like a few weeks ago, I was talking to my mom on the phone, and I was telling her I'm teaching this class, and she was like, oh, are you gonna talk about Pop? And I was like, oh, yeah, I think I am actually. And she's like, well, you should wear the hats. And I was like, well, I don't need the hats. She's like, no, you. So my mom used to teach like kindergarten and 2nd grade. So for her, she's like, okay, if you're gonna talk about Pop, like obviously you have to wear the hats. So I was like, okay, fine. Like I'll wear it. So she mailed me the hats, and then also in the mail she sent like 6 boxes of Rice Krispies, because like I guess in her mind she's like, oh, well you obviously have to like pass out the Rice Krispies treats. And I was like, it's not 2nd grade, but like, okay. So anyway, and like I don't want to eat these, because like there was a time in my life when I would eat like a pint of ice cream every day, but like I'm trying not to be that person anymore. So I have these and I don't want to eat them. So if anyone wants Rice Krispies, you can, okay, so I'm just gonna, here. Yeah, okay. There are too many, so just, yeah. Okay, I'm just gonna leave these around. Okay, so we have the Rice Krispies treats. Yeah, I guess that's my story. And there are more here, you can take some. Yeah, I don't know if I'm gonna wear the hat. Like, I think my mom doesn't realize that like this room is like right in the middle of the Harvard math department, and like I don't know if I want to just like do this, but yeah, I don't know. Does anyone want to wear the hat? Gloria, do you want to? Okay. You could also wear Crackle. Which one? Okay. Someone want to wear Crackle? Okay, no one's gonna wear Crackle. Okay, nice. Okay. Anyway, yeah. So this is Pop. Right. Okay, so let me tell you about Pop stack sorting. Where do I start? So back in the 60s, there's this guy named Donald Knuth. He's still alive, but he decided to write this book called The Art of Computer Programming, in which he like basically initiated the study of like the analysis of algorithms and like computer science and stuff from like a mathematical point of view. And he came up with a bunch of these like sorting algorithms and various data structures. And one of the things he came up with is this thing called a stack. And it's basically this like object that you can use to sort a permutation. And then in 1990, there was this guy Julian West, who was a grad student at MIT, and he defined like a deterministic version of this stack sorting thing. So this is a function that sends permutations to permutations, and what? Okay, so this is some function that sends permutations to permutations, and okay, so I'm not going to tell you about stack sorting, because that's what West was doing. This is Pop stack sorting, which is different. If you want to know about stack sorting, though, I'm giving a talk in the Open Neighborhood Seminar tomorrow at 4:30, which will be about stack sorting. But this is going to be different. So this is Pop stack sorting. So let me tell you how this works. Okay, so I'm going to define a function Pop, which will go from Sn to Sn. By sending, okay, this might not make sense as I write it, but I'll give an example. Sending a permutation greedily through something called a pop stack. Okay, let me give an example of this. So the stack looks something like this. So this thing is a stack, and the point is you can like put numbers inside of this. Actually, okay, so no one actually does this, but I'm gonna like indicate that this is not the same as a stack. I'll draw a little spring there, so you imagine like it's a pop stack, which means that the spring is gonna like pop everything out. So what you do is you're gonna start with some permutation. So let's say we have, okay, what permutation do I have? 5, 4, 2, 3, 6, 1. Let me keep track of which permutation I'm starting with. So I have 5, 4, 2, 3, 6, 1. And what I'm going to do is I'm going to take the leftmost number up here and I'm going to push it into the stack. But the rule of the stack is you can't have something big sitting on top of something small. You're not allowed to have a number sitting on top of something smaller than it. And what the pop stack will do is I can pop numbers out, but the rule is whenever I pop something out, I have to pop everything out of the stack. Let me show you the example, because maybe this doesn't make sense. So the 5 wants to go in, which is fine because the stack is empty, so the 5 goes in. And now the 4 can go on the 5, which is fine. And now the 2 can go on the 4. Now the 3 wants to go in, but the 3 is bigger than the 2, so 3 is not allowed to sit on top of 2. So what happens is the pop stack pops everything out. So the 2 comes over here, the 4, and the 5. Okay, like that. Now the 3 can go in. Now the 6 can't go on the 3, so the 3 has to pop out. It's going to go over here. But now the 6 can go in, and then the 1 can go in. And then, okay, we have nothing left to push in, so we just pop everything out. So the 1 comes out, and the 6 comes out, and this is our output permutation. So pop sends this permutation to 2, 4, 5, 3, 1, 6. So this is some function. You can do this with any input permutation. It's kind of complicated the way I described it, because I said, okay, you push this number in, and then this number goes in, you pop everything out, and it's kind of weird. But there's a much simpler way of explaining what's actually happening here. So what you're really doing is you're reversing the descending runs of a permutation. So a descending run is a maximal consecutive decreasing subsequence. So what I mean by that is, like, if I look at this permutation, so I start with the 5, and it decreases to 4, it decreases to 2, but then it increases up to 3. So the first descending run is this first consecutive decreasing subsequence. And then I go up to 3, and then 3 increases up to 6, so this is 3 itself is just one descending run. And then the last descending run is 6, 1. And you can see all I did is I reversed 5, 4, 2 to get 2, 4, 5. 3 just stayed as 3, and then 6, 1 became 1, 6. Okay? So let me write this down. So a descending run of a permutation is a maximal consecutive decreasing subsequence. And pop just reverses descending runs. Okay? Let me do a slightly bigger example. So if I took 6, 4, 3, 7, 9, 2, 8, 5, wait, oh, I have 2 3s here. What am I missing? Oh, 1. Then the descending runs are 6, 4, 3, 7, 9, 2, and 8, 5, 1. So pop just reverses these, and I get 3, 4, 6, 7, 2, 9, 1, 5, 8. Okay. So this actually gives you a dynamical system on the symmetric group, because you can say, well, I took this permutation, I applied pop to it, I get a new permutation. But now I could apply pop to this. If I did that, what would happen? Okay, so the descending runs would be 3, and 4, and 6, 7, 2, 9, 1, 5, and 8. So in this case, I would get 3, 4, 6, 2, 7, 1, 9, 5, 8. And you could keep doing this. And actually, eventually you will get to the identity permutation. So I'll release another p-set on Thursday, and one of the problems is to show that you will always get to the identity permutation. But here is a theorem. Okay, so theorem. This is due to Peter Unger from 1982. And it says the maximum number of iterations of pop. Oh, maybe I should say Unger was not thinking of this in terms of pop. He was not calling it pop. He was trying to solve some problem in like discrete geometry where you have like a bunch of points in the plane, and you want to know what is the minimum number of slopes that these points can determine. And he had this clever solution of like projecting these points onto a line and rotating the line in a certain way. And in the process of doing this, he basically transferred this geometry question into something about just combinatorics and permutations, and ended up basically proving this thing about pop. So the maximum number of iterations of pop needed to sort a permutation in Sn is n minus 1. And by sort, I just mean, you iterate it until you get to the identity. And I can also tell you an explicit way to find an element that requires n minus 1 iterations.
Colin.
Yes?
So that number is the same for the pop stack sorting and the regular stack sorting?
It is. It is the same for pop stack sorting and for the regular stack sorting. For regular stack sorting, this is much easier to prove, but it's kind of tricky. I mean, this is not like obvious here. But yeah, right. So if I take some set J, let me write it like this, which is a subset of the set of simple reflections, proper subset. Well, okay, let me write it as S1 through Sn minus 1. So J is some subset of the simple reflections, which is proper and non-empty. Then what I can do is I can take this element W naught of J, So remember, this is the long element of the parabolic subgroup generated by J. The point is that J generates some subgroup. Remember, that's called a parabolic subgroup. That parabolic subgroup has the longest element, which is W naught of J. And then I want to multiply this by just W naught of the entire group. So this element requires n-1 iterations to get sorted. Okay, let me do an example. So let's take n equals 5, and let's take J to be S1, S2, and S4. So this means that the parabolic subgroup generated by J is basically the permutations where I'm allowed to permute the first 3 numbers and also the 4th and 5th numbers. And W naught of J will be the long element of that, so it's basically where I put decreasing numbers into those positions. Or sorry, okay, I put the numbers in those positions into decreasing order. And then if I multiply by W naught, I reverse that. So what this ends up being is the W naught of J times W naught is 4, 5, 1, 2, 3. Okay. And if I do pop to this, so the only descending run here that's not a single element is the 5, 1, so that gets reversed and I get 4, 1, 5, 2, 3. And now my descending runs are 4, 1, and 5, 2, so I reverse those. Well, also there's 3, but that nothing happens. So 1, 4, 2, 5, 3. If I do pop again, the descending runs are the 1, the 4, 2, and the 5, 3. So I get 1, 2, 4, 3, 5. And then finally, if I do pop one more time, the only non-trivial descending run is 4, 3, so that gets reversed and I get 1, 2, 3, 4, 5. So it took 4 iterations, which is n-1. Yes?
Are those the only ones?
That's a good question. These are not the only ones. Actually, okay, that is exactly what I was going to write next. So let me write that. So this is open. How many elements of Sn require exactly n-1 iterations of pop to get sorted? So I put this on the P set for this week. You don't have to solve it because it's open, but it's extra credit. So, yeah.
Is the sequence no?
No. I mean, you can compute it for some values and you can put it into the OEIS, and I think I did this at some point and nothing came up. I don't know. I mean, I don't think people have really tried super hard to figure out what this is. And even if there's not like a nice formula, it's possible that maybe you could say something asymptotically, like a lower bound for the number of elements or an upper bound or something like that. So I think it's like relatively unexplored, but yeah, I don't think there's like a known formula or anything.
How much extra credit is
What?
it?
Oh, yeah, I mean, it'll be a lot of extra credit. I mean, I guess it depends on how satisfyingly you answer this. Like, if you get a nice, like, exact formula, then you get an A in the class. And, like, if it's, I don't know, if you say something like reasonably non-trivial, a little more extra credit, or some amount of extra credit, you know. I think the way I phrased the problem was like, say something interesting and non-trivial about the number of elements. So it depends on how interesting. Where is it?
I'll code it up right now.
Okay, yeah, do it. Okay. So here's another thing you could do. You could say, what if I start with like a random permutation? So let me, how do I want to write this? So I want to let this calligraphic dn be the average number of iterations of pop needed to sort a permutation in Sn. So I don't know what dn is, but okay, I have a conjecture, or I made a conjecture at some point, although I'm not entirely sure if I believe this anymore. But my conjecture so I made this, when did I make this? 2021, I guess, wasn't this published? Let me put like a question mark, because I don't actually know if I believe it still. But the conjecture is that this dn should be n minus little o of n. So I'll just remind you what this means. This basically means it should be n minus some quantity that is like lower order than n, or a better way of saying this is if I take n minus dn, then divide that by n, that should go to 0. So okay, I can also phrase this as, let me write it this way. So i.e., if I took n minus dn over n, this should go to, or sorry, okay, I can factor this. 1 minus this thing should go to 0 as n goes to infinity. That's the same as what that's saying. So I don't, okay, maybe one thing I should say is that I know that dn is at most n, because this is the average number of iterations needed, and I know that the maximum number of iterations is n minus 1 by Unger's theorem. Yeah. So the problem is to try to get a matching lower bound. And I don't know if the truth is actually n minus little o of n, but I think whatever the coefficient in front of the n should be, it's probably close to 1. So if it's not 1, maybe it's like 0.99 or something. But, okay. So here's an exercise that I did put on the PSET, and this is like an actual exercise that is not for extra credit. It's for normal credit. So show that dn is at least 1/2 n minus little o of n. Okay, I have let me show an animation. I don't want to have to hook this up to a screen or anything because I don't want to bother with that, but I'll at least try to just show you on my computer. Hopefully it'll be visible. Hopefully hopefully this will turn on. Okay, while it's turning on, let me start writing something else. Oh, okay, here it is. Okay, let me see. How do I make this bigger? Okay, I can't see how to make it bigger. Okay, maybe this doesn't, I don't know if you can see this. How do I make this bigger? Can you see this? It should look like a bunch of dots randomly drawn.
It
in a
does
ri-
look like a
Okay,
bunch of
that is what it is. So, how do I make this bigger?
Not see each individual dot, but
Okay,
can tell that it's.
I'm gonna, maybe I should have figured out how to use the projector. Okay, whatever. I'm gonna show this to the camera and then you can watch I don't know. Oh, it's going. No, stop. Okay. Here, camera. Okay, so I'm gonna run pop like multiple times and it starts sorting it. And it does this thing. Whoa.
Is that a Mathematica?
This is Mathematica, yeah. Okay, there it's going again. So I started with a random permutation. I'm doing pop a bunch of times, and it's like sorting it into this thing. And now it's the identity. Okay. I don't know how much this was visible, but maybe you can see this, or maybe not. Okay, there it's going. It's sorting. Okay, so that, yeah, there's that. And so, I don't know how long it takes on average, but I know it's at least this. Actually, there's something stronger that I can say. So there was a paper released this year by someone named Lichev. So this is 2023. I think not published yet, so I'll put a plus. And this shows that dn is at least 0.503 n minus little o of n. So it's an improvement on the 1/2 to 0.503. But then actually, even more recently, there was another paper by Bauer and Copenhaver. Claiming to show that dn is at least 0.6 n minus little o of n. So here's another problem that is on the P set that is open. Show that dn is at least 0.60001 n minus little o of n. Okay. And that's also extra credit. Okay, let me mention one other open problem, which I also, I think, put on the P set. But this one falls into the category of, I don't know if anyone's looked into this really. Maybe they have, I'm not sure. So suppose we choose W in Sn uniformly at random. What is the expected number of descents of pop of W? Let's say asymptotically. So in other words, you take some random permutation, you reverse the descending runs, and now how many descents do you expect this permutation to have? So there is a similar question for stack sorting, which is not pop stack sorting, and I will tell people about that tomorrow at the Open Neighborhood Seminar. There's a nice answer, but I don't know the answer for this, for pop stack sorting. Okay. So, why am I telling you about pop? Because I want to do it for Coxeter groups. So let's see, we can do that. So here's a proposition. So let WS be a Coxeter system. I guess maybe I don't have to write that because we're sort of assuming that through this class, but whatever. And J is some set of simple reflections such that the parabolic subgroup generated by J is finite. So if XS is covered by X in the right weak order, okay, so remember, this is my notation with the dot, that means like a covering relation. So if XS is covered by X in the right weak order for every S in J, then I can take the meet of this set, so X union the set of XS such that S is in J, and this is going to be X times the long element of the parabolic subgroup generated by J. So this is actually written in Bjorner and Brenti somewhere in chapter 3, although I think there's a slight mistake, which is that they failed to include the X here. You might think, well, why would I need X? Because this is a meet of like a bunch of things that are covered by X. So if I take a meet of a bunch of things covered by X, I don't also need to take the meet with X because that's not going to change anything. The issue is if this is empty. If this set were empty, then I want to include this. But anyway, in particular, I could take J to be just the set of right descents of X. Right, so basically this condition here is just saying that every element of J is a right descent of X. But I could say, well, what if J is just all of the right descents of X? So in particular, if I take the meet of X union with the set of xs such that s is a right descent of x. This is x times the long element of the parabolic subgroup generated by the right descent set of x, which is this. Okay. All I did is I just plugged in j equals dr of x. Okay, so what am I doing when I do pop? Well, I'm basically multiplying by W naught of the right descent set of x. Because W naught of the right descent set of x is just this thing that like reverses all of the numbers that are in these blocks. So like in this case, if I took this example and I took dr of x, if this is x, dr of x would be S1, S2, S4, S5, S7, S8. And so W naught of dr of x just reverses these blocks. And so if I multiply by dr of x on the right, that's exactly what pop is doing. So, corollary. If I take W, or if I take x in Sn, then pop of x is just, well, I could write it as x times W naught of dr of x. Because again, this is just going to reverse the descending runs. But this could also be written as this meet. But actually there's another way of thinking about this. So the set of xs such that s is a right descent of x, these are precisely the elements covered by x in the weak order. Right? Because that's what it means for xs to be, or for s to be a right descent of x, it just means that xs is covered by x in the right weak order. So I could write this as the meet of x union with the set of y, let's say the set of y in W, such that y is covered by x in the right weak order. Okay. I can do maybe an example. So let's say x is 5, 3, 2, 6, 7, 4, 1. So the right descent set of x is S1, S2, not S3, S4. Well, I guess maybe this is the example I had before. And then sorry. This is S3, S4. I think I wrote this down wrong, but okay. No, not S4. Sorry, okay. It goes down, it goes down, it goes up, up. Okay, so then S5 and S6. Right, okay, so S1, S2, S5, and S6. Okay. So that means that W naught of dr of x is what I get by like reversing these blocks. So 3, 2, 1, 4, 7, 6, 5. And then if I take x times W naught of dr of x, well, I just multiply this permutation by this permutation, and that's just going to give me 2, 3, 5, 6, 1, 4, 7. And so you can see all I did is I just reversed the descending rungs. Okay. Okay, but everything I've written here, like this, makes sense for any Coxeter group. I didn't need X to be in Sn, it could just be in W. So, okay, I guess the reason I wanted to tell you about this is because I think it's sort of this is like one of the themes that I wanted to get across in this class, where you can take some combinatorial thing that people have looked at. So people had already studied this pop stack sorting map on the symmetric group. People had asked questions like, okay, how many elements of Sn require 2 iterations to get to the identity? How many require 3 iterations? Things like that. There's this theorem of Unger that I erased that says the maximum number of iterations is n minus 1. So you have these like combinatorial questions about permutations. And you can say, oh, well, I can just formulate all of this in terms of Coxeter groups, and I can ask the same questions about Coxeter groups now, and see if I can then answer them maybe in some kind of Coxeter theoretic way by using like reduced words and descents and more algebraic ideas, or geometric if you think about it geometrically. Okay, so we can define, so I'll still call it pop. But now it's just from any Coxeter group W to W by pop of X is just the meet in the right weak order of X union the set of Y in W such that Y is covered by X. So it's the same thing. And the meet here is, again, in the right weak order. Right, so we're using the fact that the weak order is like a meet semilattice, so I can take a meet of any set of elements. And this is equal to X times W naught of dr of X. But actually, this definition makes sense, like this part of the definition makes sense for any meet semilattice. I guess, let's say, locally finite. So more generally, if L is a locally finite meet semilattice, we can define pop from L to L by the same exact formula. So by pop of X equals the meet of X union the set of Y in L such that Y is covered by X. Okay? Let me give an example of this. I guess I'm almost out of time. Okay, so here's an example. I'll just draw a lattice. So there's some lattice, and I can draw what pop is doing to it. So if I apply pop to the top element, there are two things that are covered by the top element. Okay, so I should say what I'm really doing is I'm taking the meat of the things covered by x. Here I also wrote x, but that doesn't actually matter unless x is the bottom element. That's the only reason for having this in here. So really what I'm doing when I apply pop to the top thing is I take the meat of these two elements, and that would be this element here. So pop sends this top element to here. If I apply pop to this element over here, well, it only covers one thing, and the meat of one thing is just that thing. So I just go here. If I apply pop to this element, it covers one thing. So I just go down to that one thing. If I apply pop to this one, it goes to the bottom, because it's the meat of these two elements. Pop of this is just going to be the bottom. Pop of this is the bottom. And then finally, pop of the bottom element. So now that's when I actually use the x here. I'm taking just the meat of the bottom element itself, which is the bottom. So the bottom is just fixed. Okay? Okay, let's see. So I guess next time I will tell you a generalization of Unger's theorem, which is, so remember he said that the maximum number of iterations needed to sort a permutation in Sn is n minus 1, and I'm going to define something called the Coxeter number of a Coxeter group, or a finite Coxeter group, let's say, and it'll turn out that you can generalize this n minus 1 fact to any finite Coxeter group. Actually, I can define the Coxeter number now, and then maybe that'll be the end of today. So, okay. So suppose W is finite. The Coxeter number of W is, so it's typically denoted by H. It's this number H, which is just 2 times the number of reflections of W divided by the number of simple reflections of W. Okay. And as an example, in Sn, so for W equals Sn, what is the Coxeter number? Well, it's 2 times the number of reflections in Sn. In other words, the number of transpositions is just n choose 2, because there are n choose 2 ways to choose the numbers I and j to get a transposition I comma j. So this is n choose 2. And the number of simple reflections is n minus 1. So this is 2 times, well, n choose 2 is n times n minus 1 divided by 2, and that's divided by n minus 1. And if I simplify this, I just get n. So the Coxeter number of Sn is n. And I'll tell you more about Coxeter numbers next time, but that's all for today. I want my hat back. What? Yeah.